Hello and welcome. In this video we will discuss Stokes' theorem, another one of the big integral theorems of vector calculus. Stokes' theorem relates the line integral of a vector field over a curve C to the surface integral of the curl of the vector field over a surface having C as its boundary. An oriented surface is a surface having a consistent choice of normal vectors, typically pointing toward the outside of the surface. Then the boundary of the surface is a curve, and the positive orientation of this curve is such that if you walk around it standing upright in the direction of the normals, then the surface is always on your left. Since this theorem involves the curl, let's recall that the magnitude of the curl at a point is related to the amount of rotation that the field induces. We have a formula for computing the curl, but it'll actually be easier to understand Stokes' theorem if we quantify the curl in a different way. We'll measure the amount of rotation by computing the line integral of the field around a small loop enclosing the point of interest. The dot product in this integral can be interpreted as a projection, that is, the extent to which the vector field lies along the same direction that the curve is traversed. If the curve lies mostly in the same direction as the field, then a particle on the curve experiences more push, which will in turn yield a faster rotation. The line integral around the loop adds up all these small pushes to give the total extent to which the field flows around the loop. In fluid mechanics, this quantity is often referred to as the circulation of the field around the loop. Again, the circulation represents the net amount of push that the field exerts around the loop. So the larger the circulation, the more rotation will be produced. To capture the idea that the curl is related to the rate of rotation at a single point in the field, we'll consider the circulation of the field for smaller and smaller loops enclosing that point. As the length of the loop shrinks to zero, so will the circulation of the field. So circulation alone isn't helpful. However, the ratio of circulation per unit area enclosed by the loop will be meaningful in the limit as the enclosed area tends to zero. Now, the larger the circulation per unit area, the more rotation we expect the field to induce at the point. This is where the curl comes in. Let n hat indicate the orientation of the paddle wheel in the field. Then for a curve around the wheel, in the plane perpendicular to n hat, the curl is related to the circulation per unit area. This agrees with the idea that the curl vector provides the orientation of the paddle such that the rate of rotation is maximized. If n hat is in the same direction as the curl, then this dot product is as large as possible, and the circulation per unit area is maximized. If n hat points in any other direction, then the wheel doesn't feel the full effect of the field, and the rate of rotation will be diminished. We've taken a long detour to formulate the curl in terms of a line integral, but this will make it easy to work out Stokes' theorem. Let C be a curve serving as the boundary of an oriented surface S. And imagine tiling the surface with a bunch of contiguous loops, oriented counterclockwise, with an outward-pointing unit normal vector, n hat, positioned at a point in the middle of each of the loops. Each individual loop encloses a small area, delta S, on the surface. So the limit definition of the curl gives a reasonable approximation for very small values of delta S. Multiplying the area element to the other side and summing up over all of the loops gives this expression. Here's the key observation. Nearly all segments of the individual loops are traversed twice in the process of computing all the line integrals, each time in an opposing direction. As was the case for Green's theorem, all segments cancel each other out except for those along the boundary curve, because each part of the boundary curve is traversed only once. So the sum of the line integrals collapses into just the single line integral around the boundary curve C. Making the size of the mesh smaller and smaller, the summation becomes a double integral over the entire surface, and the approximation becomes exact, yielding Stokes' theorem. Physically, you might read this mathematical result as the net swirl of vortices on the surface is equal to the circulation around the boundary of the surface. That was a lot to absorb, but please take a moment and empathize with how I must feel right now. A couple concluding remarks. First, Stokes' theorem is another generalization of the fundamental theorem of calculus. In Calc 1, the fundamental theorem relates the integral of a derivative over an interval to a calculation involving only the boundary of that interval. Here, we have that a surface integral of the curl is equal to a line integral around the boundary of the surface. The curl is a derivative-like quantity, and the line integral is a computation involving only the boundary. These theorems are indeed similar in structure. Another very important thing to note is that the surface S didn't have to take a specific shape. The theorem is true for any reasonable surface having boundary C. In applications, this is the main power of Stokes' theorem. Since the theorem does not depend on the surface having a specific shape, one can use Stokes' theorem to derive physical laws in a much more general context without assuming that the objects have a regular shape, like a sphere or a cube. You should definitely expect to encounter Stokes' theorem in future physics classes, especially in electricity and magnetism. For example, consider Faraday's law of induction, one of Maxwell's equations modeling the behavior of electromagnetic fields. Faraday's law relates the circulation of an electric field in a closed circuit to the time rate of change of magnetic flux through an enclosed surface. I'll leave the details to your physics class, but Faraday's law, as with all of Maxwell's equations, can be formulated in either integral form or an equivalent differential form. Each of these formulations has its advantages, and the equivalence of these forms of Faraday's law is due to Stokes' theorem. So look forward to that, and thanks for watching.